He's a multi-gold producer with over 500 million streams, and his music has been featured on TV shows, movies, and video games. And if you've watched my channel for even just a little bit, you've definitely heard his work on my videos. But what you might not know is when he's not in the studio, he's in the lab as a synthetic organic chemist cooking up novel medicines to treat cancer. Today, we're going to merge those two worlds and see how one man masters the chemistry of music and molecules. DJ Grumble, it's an honor to have you here, man.
Yeah, dude, glad to be here, man. Glad we can make it happen. It's super cool to talk to a fellow chemist and, somebody who also enjoys the same type of music I do. So yeah, let's do it.
You started creating music in your teen years, right? Growing up in Boston. Tell us a little bit about your underground hip hop days and, how you started developing beats.
I would say like hitting puberty, right? So like 7th or 8th grade. I was listening to a lot of like Linkin Park, Limp Bizkit, like the rap rock that was really popular in the early 2000s. A lot of those bands had DJs, right? And they had the Zigga Zigga sounds. And I was interested in that part. I was like, how are they doing that? Linkin Park collaborated with a group called the Executioners, which was like a 5-man turntable group, and they would all put a song together, like all playing the turntables at the same time. So they were like using the turntables as an instrument. So there was like a crossover, and I was like, oh, like there's this whole hip hop world, right? So I started listening to hip hop, and I was like, how do I make the beats? I'm completely mystified as to how people make the beats that sound like this. So I got to figure this out. My first turntable, my dad got for me from like a flea market for like $20 or something, and it was like a crappy old belt drive turntable, and it had a classical record that was like on it, and it came with the turntable. And so I made my first beat out of that classical record because I was like, well, I need a record, right, to make a beat.
I remember Mr. Hahn from Linkin Park,
Yeah, Mr. Hahn, yeah.
Dude, my favorite track on Hybrid Theory was just his breakdown, like where he's just going nuts, man.
Yeah, it's called Cure for the Itch, and I remember like ripping the MP3 for that song. Like I found it on like Napster or something. I remember like listening to it. I was like, how do I make the beats like this?
Yeah,
and
for sure.
So that, I started researching, different producers and like listening to different music and kind of figuring it out, how they were doing it.
That's really cool that you mentioned your dad buying you this really simple setup. Before the days of social media, you have YouTube and MySpace and Facebook, all that stuff. You were going and buying records from like old Salvation Army thrift stores and really humble beginnings. And I wanted to get your opinion for any aspiring producers that might be watching, who think you need some kind of thousands of dollar elaborate setup to start. What advice would you give them to kind of start dipping their feet in the water of producing?
Oh, yeah. I mean, that's the easy one, is because you don't need anything really now because the barrier to entry is so low. Because like when I started, you actually needed to have like some technical know-how, right? To get a computer, connect to the internet, get the software that you needed to make beats. But now you can just download everything as an app on your phone. Like you just need a phone and Wi-Fi. There's an app called BandLab that you can just make entire songs on. My advice when you're starting out is just do what works for you. It doesn't have to be really expensive equipment. It's just whatever works best with your creative process.
Yeah, no, that's completely understandable. I tried making beats 15 years ago in GarageBand, with a very limited like kick and snare set. It was very tinny sounding and garbage, so I just stopped.
That's actually a good piece of advice, is like GarageBand is free, like on pretty much all Macs. A lot of producers use GarageBand to make hit records. I think Steve Lacy's used it, or I know Madlib has used it. So there are a lot of major producers who use simple software like GarageBand because it's more about like your taste and how you're arranging the sounds, and the software is just a tool to arrange the sounds how you want.
You've had this social media campaign going on for a while, make a beat a day until you run out. That's kind of a really lofty goal to have. And so I wanted to ask, is it motivating you to stay active and relevant in the industry, or is it giving you undue stress, in your daily life?
The campaign started as a way just to like promote the vinyl that I had coming out and like try to drag traffic to the website where you can still get it at ft2024.com. And I was like, okay, I need to come up with a content strategy. The Daily Beat is just a way that I can like kind of be consistent and like show up on people's social media feeds. Like friends of mine will be like, oh dude, like I see you all the time, like on TikTok or like on YouTube shorts. Your visibility increases and you get more traffic to, you know, wherever you want to send people. In my case, usually Spotify.
For the viewers, FT 2024, that's DJ Grumble's Freestyle Tools series. If you want to start somewhere, 23 and 24 are great. Those are my favorites.
You go viral if you're the best at making people like stop scrolling and like watch what you're doing, right? And so I was like, what's a format that I could do that I'm not like dancing for the camera like a clown and it's still keeping like the music first and foremost, but it also looks cool and like people probably like stop and like for a second at least listen to it. It can be stressful sometimes, but I've learned how to like manage it because it doesn't take that long. Sometimes I'll like have to do like 10 or 20 takes because I keep screwing up the drop and it's like not quite on beat. That's the part you don't see.
We'll point our viewers to a recent interview on Toru's podcast, Producer Head, for a deep dive into the musical aspect and all of your great advice and history and producing and getting paid on time and all of this other awesome information that's in there. I want to get into some chemistry discussion if that's cool with you now. Before we get started though, the whole left-brained versus right-brained theory has been debunked by neuroscientists, right? We know that's not true, and you're a living proof of that. So how do you kind of mentally shift gears from making beats to balancing equations?
I view them as complementary, where like the science, I'm kind of like constrained, you know, because I'm trying to find a solution, and the music is open-ended, and I get to use my brain in a way that's like less of like a test, so to speak, and more of like open-ended.
Proper harnessing of entropy in both cases, right?
Mm-hmm. Yeah, exactly.
Yeah. No, that's cool. I totally get it.
On an average day, there's like a list of like at least a dozen things that need to be troubleshooted. And it's like I'm working in order of, you know, the thing that's the most stuff and, you know, solving them one by one, right? And so like that's a different kind of work. You're digging at like objective reality, like is the molecule that I made the actual molecule that I think it is or not, right? And so that's true or not. Like there's a yes or no answer to that. But with the music, I mean, that's like more open-ended, right? It's like, does this sound good to me? You know, you can make a lot of things that sound good to you. It could be like funky, or it could be like smooth and slow, or it could be like outer spacey. You have more freedom because there's not the constraint of there being like an actual like solution that you're working towards necessarily. It's more of like trying to make something that is enjoyable. Usually I find like if I enjoy it, then you just kind of know when you hear it. It's like an intuition you develop over time, like your taste in music, right?
To switch it up a little bit on you, I have a little quiz that I've prepared. I think it'd be interesting to discuss. Basically, we're going to be comparing sets of molecules, two very similar molecules with very small changes, and we're going to ask you which one has the higher melting point and why. So you can give us your take on an intro level OChem explanation. That sounds cool to you?
Yeah, let's do it.
All right, awesome.
Yeah, I find these really interesting because they're so very first principles.
Naphthalene versus quinoline.
Well, this one I know from personal experience because I've held both of them in my hands. Naphthalene has a higher melting point.
95 degrees.
Yeah. So yeah, just substituting the nitrogen. And for me, I mean, this is a simple one. You've broken the symmetry of the naphthalene ring by introducing that nitrogen. There's no real planes of symmetry now in that molecule. I mean, I guess there's one through the plane of the screen. The plain naphthalene molecule can pack much easier than the quinoline. And the nitrogen lone pair is going to interfere with the pi-pi stacking as well. Yeah, I think that one's like a pretty straightforward one.
Awesome. Let's do another one. Norbornadiene versus norbornane.
Pretty sure I've seen norbornane as a solid before. I'm going to go with norbornane. Okay.
Norbornane is correct by quite a bit.
All right, 100 degrees. It's kind of counterintuitive. One of the classic sophomore orgo labs is where you like hydrogenate trans fat and it goes from a solid to a liquid. Because of the unsaturation, they can pack together and clog your arteries, right? So that would make you think that the norbornadiene, you know, maybe can do some pi-pi stacking and pack better. But I think in this case, both alkenes are strains and they probably can't pi-pi stack. effectively due to the bridge. Norborneans can do inverse electron demand Diels-Alders, so they are pretty, like, have a very different character, sp2 character, than just like a regular alkene.
All right, next one. Nicotinic acid and picolinic acid.
I'm gonna pick wrong. It's nicotinic acid, right?
That's your final answer?
Yeah, final answer.
It is nicotinic acid.
Yes. Okay. And the reason I said that was just because I suspect for picolinic acid that you can have intramolecular hydrogen bonding with the carboxylic acid and the pyridine, whereas with nicotinic acid, it's too far away that the hydroxyl group can't be occupied by the same nitrogen lone pair or hydrogen bond with it. So they would have to bridge each other. So that would make them more likely to pack better as a solid versus a picolinic acid.
Competition between intermolecular and intramolecular forces wins out, right?
Exactly. Mm-hmm.
All right, awesome. I have one more for you. You've been a great quiz recipient so far. Last one now. 1,2,4-triazole versus 1,2,3-triazole.
Yeah, this one is also like a big stumper because I want to say 1,2,3-triazole, and I work with 1,2,3-triazoles a lot because I do a lot of copper-free clip chemistry. I'm pretty sure it's a liquid at room temperature. I don't know. Yeah, I'm gonna go with 1,2,4 is the higher melting point.
1,2,4, final answer?
Final.
That's correct. 4 for 4, man.
Okay, we got it. And for this one, I really don't have a good explanation because literally it's just you've moved a nitrogen just one position over. You've created a symmetry plane in 1,2,4-triazole. If you assume that hydrogen or the proton can just kind of evenly skip around the nitrogens. But I think also 1,2,3-triazole, if you look up literature on benzotriazole, which has a benzene ring fused to it, they tend to align in like a linear fashion. And so my only guess here is that the 1,2,4-triazole is capable of forming maybe more of a 3D crystal structure than the 1,2,3. I think these are good questions because they just make you think about the nature of molecules and how they interact with each other. Good quiz, very nice.
Solid, man. Good job. Getting into a little bit of your career experience now. So you've worked in a large pharmaceutical company and you've helped create and commercialize, I think, right? Novel therapeutics for cancer.
Yes, we're commercializing now, yes, at the startup.
Can you tell us, within the bounds of your legal limits of what you can share, can you tell us kind of the coolest chemistry breakthrough that you've had in your pharmaceutical career?
Yeah, I can speak to a bunch. I don't know if I touched on this a lot in the interview with Toru, just to not confuse the audience, but I also worked quite a bit in electronic materials. A lot of my expertise is in like nano fabrication, like making really small stuff. But man, I would say probably one of the coolest pharmaceutical discoveries to date was that a platform that our group had been using for a long time as like a promising therapeutic, but had really just remained, as academic papers and not really in trials, was figuring out that replacing the outer shell of ligands on the nanoparticle with similar but just neutrally charged ones enabled the nanoparticles actually to circulate in the blood for like a half-life of like 30 hours or something like that. It was like almost more than we could measure with the length of the experiment. It basically enabled us to create a startup based on the technology that my colleague and I initially discovered in graduate school. That was like over 10 years ago. And then since then, there have been sufficient developments in like both our research and what is offered by other biotech companies, like in types of conjugation chemistry that's available, that we're actually like, oh, we might actually be able to implement this in a way that's medically relevant. That's what we're doing now. We want to approach like pharmaceutical partners and be like, hey, look, we came up with this delivery platform, for chemotherapy drugs, and it has a much higher safety profile. Your drug isn't going to damage organs that it's not supposed to. You might have poured billions into this drug that failed in like phase 3, and actually you might be able to rescue it. And so that's like the value proposition. Basically, we're in a preclinical phase of the cancer research, but we're working with very common cancer drugs. For example, doxorubicin is one of them. Monomethyl auristatin E, which is a topoisomerase inhibitor. or microtubule inhibitor. I'm not a biologist. It kills cancer cells. And then like camptothecin derivatives like SN38, that's the main metabolite of irinotecan, which is one of the frontline cancer drugs. Our approach is different because unlike most of the like sort of advanced cancer therapies that are out there now, which are mostly like monoclonal antibodies, where they have an antibody, it's targeted to some external cell receptor that's known to be overexpressed in cancer cells, and it has a drug attached to it with some sort of like cleavable linker. So you get injected with the antibody, and some of it gets to the tumors and, you know, releases the drug and kills it. But yeah, getting antibodies to have good blood circulation time without, you know, getting recognized by your immune system is pretty tough. Essentially, our technology is like it's the only one where we're actually going inside the cell as the first step, and then we're actually reading the mRNA that's present in the cytosol, and if we detect the cancer-related gene that's being, you know, actively transcribed in that cell, then the nanoparticle is going to wreak havoc on the cell and release a cancer drug and screw it up. And now we're kind of proving out that selective release mechanism through our animal experiments and showing that, yes, like it's only releasing in the cells that have cancer. It's not releasing the payload in any other cells.
Dude, that's amazing, because selectivity is such a big issue, right? And achieving selectivity and understanding cooperativity with those huge molecules is still such a challenge. I mean, no one really knows, you know, exactly what's going on, even the experts. The beyond rule of 5 chemical space, like PROTACs and all that stuff, is huge these days. And for you guys to be able to target mutant transcribed RNA only in cancer cells, man, that's huge. That's awesome.
Yeah. The technology has already kind of been proven out. We've done it in like petri dishes, like because you don't have to release just a dye, you know, or a drug. You could release a dye, you know, and just look at it under a microscope in a petri dish, and you know you could have healthy cells and cancer cells and dose them with the particles, and you can see that the cancer cells, they're massively saturated with dye molecules. Like if we use, for example, gold or something as the core that quenches fluorophores, you can have them on the gold or like near the gold core and quenched, and then once they're released, they turn on essentially. So you can have like the turn on detection of cancer cells, just like even in a tissue sample or a cell sample. So that's like our lower hanging fruit, is to be able to create like a benchtop diagnostic device that can do that, but like with much higher sensitivity than the current state of the art. And so we're doing that with like metal enhanced fluorescence. Essentially, is instead of releasing one fluorophore with a binding event, it releases a nanoparticle that has 100 on it, and it's also enhancing all of those fluorophores by 100 times.
They light up like a nuclear reactor, is what it sounds like.
Yeah, a lot of it is based on a paper that I published in Agavante Chemie in 2014. We wanted to replace the gold ultimately. Like even way back then, the FDA wasn't all too thrilled with the idea of just injecting people with noble metal nanoparticles. And so my PI was like, all right, just make it with like iron and like something edible, so it's like biocompatible. That was like literally the task. And so I went through a bunch of iterations of it, but I ended up making an iron 3 chelating ligand. And so it's a central benzene atom, and meta substituted to it are 3,4 hydroxypyridinone rings. And so they have a carbonyl group vicinal to a OH group. Each one of those chelates iron, and the iron forms trivalent complexes with those type of chelators. So it forms a Fe2 L3 stoichiometry. So if you just mix them, if you mix the ligand with iron in water, the ligand's soluble in water if you just add a little sodium hydroxide, because the OHs are acidic. Like they're like kind of phenol and pKa, about 9 to 10. Okay. So you can dissolve it in like weak sodium hydroxide, add some iron nitrate, which is like easily displaced, and then the nitrate salt is easily displaced by the bidentate chelators. And then it just forms this basically insoluble brick dust of iron that is bridged by organic ligands. I basically just figured out if you do it dilute enough and if you get the conditions right, you can get them to form nanoparticles that are like between 10 and 20 nanometers or so. And so we started using that as the scaffold instead of gold and silver for like the therapeutic version, because ultimately the components that went into making the scaffold, like your body can metabolize, and they're not harmful. It's not going to metabolize to anything that's, you know, by cytochrome P450 that's, you know, known to be toxic. So it was done sort of like with a medicinal chemistry approach. But yeah, it's basically two molecules of deferriprone, the iron chelating. It's an iron chelator that's given for iron overdose. Like if you accidentally like ate a whole thing of iron supplements, that's what they give you. But it's two molecules of that bolted meta to each other on a central ring. And then meta to those is a dangling azide angle. And so the azide is how we just attach stuff to it. So you have these, polymeric iron organic nanoparticles that are stable in water, and they have azide handles dangling off them. So we mix basically whatever surface composition we want. We have a mixture of ligands that are terminated in strained cyclooctines like DBCO or BCN, and so they just essentially click and self-assemble around the core, and that's how we make the final construct. But that's what we're actually applying to with the FDA and like disclosing to them is our therapeutic products. And so they're going to need some like really rigorous characterization. Like, they're going to need to see the PDIs of like the nanoparticles, that it falls within their range and all that stuff. So, all that stuff is later in the pipeline, but we're sort of anticipating, what could be the failure modes, what could the FDA take issue with, what could go wrong with the actual construct itself in the body. So, we're always trying to just failure-proof it and think of ways that it could go wrong,
Mm-hmm.
I tell everybody it's been like a GTA mission working on this because it's like, something that you thought was originally just going to be like just an academic paper. Oh yeah, it got 100 citations, nice. And then suddenly you're commercializing it and you're scaling it up to inject into, monkeys. I'm like, oh, it's real now. Uh-oh.
With your experience in big pharma and your experience in a small startup, those two environments are vastly different in your timelines and in your decision making and the number of different hats you have to wear. Could you give our viewers a little bit of a pro and con or like a compare and contrast between those two environments?
Yeah, absolutely. So yeah, I've worked both like Fortune 500 and like startup, with like our current team has like 5 people to give you an idea of the scale of the team. Fortune 500, being a W-2 employee and like, doing research for another organization, it's still enjoyable if you really like chemistry and you like making an impact. I think the work is still enjoyable, but it's really the work environment that is not, at least for me, like, having to dress a certain way every day at the lab and having to go to arbitrary like work events and like, have my schedules full of meetings every week that, could be emails, having to make PowerPoints to show the upper level management that they don't understand what we're doing. A lot more of your time is consumed with stuff that you don't care about, and you just got to get used to it. In a startup, there's not so much rigid adherence to like, you have to be here at a certain time and you have to clock out at a certain time. It's just like, dude, if you're burnt out, just go take a walk or go home, I knew that the hours would be more than just a regular 9 to 5, but maybe there's some days I have a lot more energy than others and I can just bang out a ton of stuff, right? And
judging an employee's productivity by their deliverables and not micromanaging their time, man, in my opinion, that's the way to go. You gotta just give the person, you're a PhD, right? Just give you freedom to solve the problem your way, meet the milestones, and you're good to go. Who cares if I'm not there at 8:30 a.m. on a Sunday?
You have so much more freedom in a startup, especially if it's like with your colleagues that you already know. We've known each other for over 10 years, right? So we get along, we actually live together. It's pretty cool, honestly, to just work on a project with your friend that you both believe in. And you're like, if we just work on this, it's going to be hard, it's going to suck. At the end of the day, with enough brute forcing this, it's solvable. There's nobody to pick up the slack for you at a startup. It's like you are the only person. I think that's the nice part about being in a startup is you get to focus a lot more on like solving what's important to you specifically. Our lead investor actually strung us along for a little bit, and I first arrived here and we still hadn't gotten our first check. And so I'm buying like labware from Amazon on my personal credit card. And like I bought, for some reason I could buy like toluene and stuff on Amazon too, which seemed odd to me.
Yeah.
But like I was just buying stuff like with my personal credit card and like doing reactions and stuff, and finally like the check came through in February, like for our first like $500,000. We were like, okay, thank God, all right, we're good for a little while. And then it's like monkey see, monkey do. Like once somebody invests, then like everybody else starts wanting to invest.
You all heard it here first. I mean, if you want to do medicinal inorganic chemistry and some cool 1,3-dipolar cycloaddition click chemistry, you could probably do that in pharma. But if you want your bank statement to look like Breaking Bad, you should probably join a startup.
Yeah, exactly. But the craziest story is that somebody who only knows me through SoundCloud messaged me on Instagram. He was like, "Oh, I see that you moved to SF. Like, I'm actually out in the Bay too. Like, I'm at like a software startup. Can we hang out sometime?" Basically, like, he just wanted to kind of see the beats and the process. I was like, "Yeah, just come over one weekend or whatever." And we got to talking, and he got talking to the co-founder, Will. He was like, "Can you send me your deck? It sounds really interesting." And so we sent him our technical deck, and he invested $20,000, and then he got a friend of his from Stanford, who's like a Bitcoin millionaire, to invest another $40,000. And these guys don't even know, like, they just know me through the beats on Spotify. Yeah, overall, like, I mean, I think the momentum's been positive. Like, we haven't had really any like project killers so far. Right now, the biggest consternation is DNA synthesis, because we need to be able to scale up to make enough DNA for like a monkey dose, which is, we're talking, a mouse is like 25 grams versus like the smallest monkey is like 2.5 kilograms. So the scale increase is huge. And so we bought a synthesizer that can handle that scale, but has required so much troubleshooting that's been almost all we've been doing for the last few months, is like doing DNA synthesis runs and then like troubleshooting. Okay, why does it look like why did we only get 30% yield? Like, why are all these truncation sequences in the product? Stuff like that, So that's currently, but I think we got it now. Actually, the stuff I'm purifying right now, I think we figured it out. We install a tiny camera inside the synthesizer so you can watch it remotely and watch it dispense. And so we can like monitor it even if we're not at the lab and make sure it's like dispensing into the right columns and like the right reagents.
Yeah.
So yeah, I think we finally got it. But yeah, that was like the main consternation, was like something out of our hands. It was just a machine that was not calibrated properly. Things would randomly fail on it. So we kind of figured out like, oh, okay, yeah, we need to fix this thing, we need to fix that thing, etc. Because we've discovered other interesting things along the way, not just the primary things we're working on. We're like, oh yeah, like that could be a product. My colleague developed a custom, very high scale gel electrophoresis DNA purification method where you could put like an entire 10 micromole synthesis of DNA on an electrophoresis gel and run it and catch just the band that you want. And it's like better than HPLC purification. And like, dude, I was like, dude, you could like 3D print those and sell those probably, and people would buy them. You know what I mean? Life sciences people. So yeah, I mean, just in the course of doing our work, like we've discovered a lot of like really, like just through serendipity, just a lot of really unusual stuff, like silver enhancing dyes that we didn't expect to, or even just like certain molecules like stabilizing gold and silver nanoparticles in ways that we didn't expect. And like makes them super stable to the point where you can like freeze and thaw them and they still come back, into solution just fine. But it's normally like if you try to do that to a solution of gold particles, like they're dead. If you like put them in a negative 20 freezer, they're not gonna like that. But yeah, so we're like, man, we could like, that's like a really good noble metal protectant molecule. Like we should just like formulate that. I'm sure like people who make like copper pipes would probably buy that, because we tried it on like copper nanoparticles and like silver particles, gold particles, because we use cyanide to dissolve gold and like release the surface ligands when we want to quantify them. And I was trying to kill these particles with cyanide. I'm like, dude, it's not working. What the hell? And like apparently, what this molecule that we came up with was it made such a good shell around the noble metal that it was resistant even to cyanide. That I had to like heat it to like 70 degrees for like 2 days to get the gold to dissolve. So I'm like, yeah, maybe this could be like, we could sell this as like, 1% solution in freaking toluene is like a corrosion inhibitor for piping or something, right? We've tried to keep our eyes open for like anything adjacent to what we're doing along the way.
My viewers know me as a computational chemist, and I have to ask, have you collaborated with computational chemists in the past, and what is your overall opinion of the discipline?
So actually, so the guy who does most of our cell culture, his degree is in computational chemistry. I guess he picked up a ton of cell culture stuff along the way, like through postdocs and stuff. I actually do view it as extremely valuable because there's only so much as a human chemist that I can visualize in my head, especially when it comes to like complex stereochemistry and things like that. And so, like, being able to build a model of a molecule that I'm working on, especially if it's like a very complex molecule, like maybe with like a hydration shell or it's like a nanoparticle, something with the computational power that I cannot imagine in my brain. I think computational chemists are absolutely essential. But we actually trademarked nano AI, not for any particular reason, just because VCs just kept asking us, "Oh, are you going to put AI in this?" Because like that's what's hot right now in Silicon Valley. And so we just trademarked it. Just so we have a slide called Nano AI, and it's like, yeah, the Nano AI is going to identify the right cancer sequences or something. I don't know. And even with like computer aided design, even of like small molecules, like a lot of questions that we have that are really only answerable by experiment. Is the ether linkage good enough? Or is it gonna like, is this gonna get chewed up, by esterase enzymes? Is this like a substrate for an enzyme? A computational chemist might be able to screen it against an enzyme panel and tell me, or, should I make some other kind of, should it be an amide linkage or should it be like a carbonate linkage? Putting that linkage is gonna twist it out of the binding pocket. We don't know until we try it, right? Like currently I'm modifying the variety of cancer drugs so that they can be attached to our system. And it's like, well, based on my research and what I know about where they fit in the binding pocket, okay, I'm choosing an attachment point that I don't think is going to affect its activity, but I don't know until we try it. But, a computational chemist might be able to tell me, no, that's going to totally screw the orientation. You shouldn't do that.
That's cool to hear your respect for comp chem, I mean, not everyone has that, so it's definitely cool to hear your perspective on that.
There was an incident where I accidentally caused the trimer of triethylacetone to crack in one of the chemical fabs at Dow on accident. Apparently it smelled so bad they evacuated the entire chemical fab.
Cool, man.
I didn't get in trouble though. I blamed it on the undergrad.
Ooh,
no harm, no foul.
That is harsh, man.
I don't throw people under the bus like that. What's your favorite pharmacophore, or what's your favorite bioisosteer?
Maybe like replacing an acid, like a carboxylic acid, with like a tetrazole. I was always kind of like really intrigued by that.
That's a pretty slick one, yeah.
It always kind of astounds me that would be an isosteer for a carboxylic acid, but I can see it, but at the same time, it's kind of bizarre.
Yeah, that's a good one. That's one of the ones that you wouldn't expect. Another one is like cubane or other really small strained hydrocarbons replacing for phenyl. Why the hell are you trying to make that like propeller-shaped molecule in the first place?
We chatted a lot about your scientific career, your music career. I just wanted to wrap up with a few quick questions for you, just to kind of get to know you a little more personally. What is your favorite car that you've ever driven, and what is it about that car that makes a beat sound just right?
Ooh, okay. Would you consider yourself a car guy?
A burgeoning one, yes.
Okay. Oh, that's hard to answer, but I would say probably one of my favorite cars that I've ever driven would have to be, honestly, I would say the Chevy Camaro. And I just say this because I associate it with a good memory, because I took a trip to LA to do some music stuff, and this is right before the pandemic, before everything shut down. And so it felt like the last week of freedom before everything just became static. I remember specifically I was I'm gonna rent a cool car, and I got a V8 Camaro with a drop top roof or whatever. And man, that thing would just, you get on the on-ramp and you're already at highway speeds by the time you're entering the highway. So I mean, just in terms of pure power, and the fact that you can get the V8 for actually not that much money, that's probably gonna be my next car, honestly. And yeah, the beats sounded good in it. Yeah, the car test is important because usually before I put something out, I'll test it in headphones, just on my phone, because a lot of people just listen to music like this on their phone, on AirPods, and then I'll also listen in a car, just to try to catch anything. Sometimes you can unmask clashes and frequencies with certain sound systems that you might not catch on your headphones or whatever. Let's go V8 Camaro, all American classic.
We'll wrap up with a little rapid fire segment, all right? So I'll give you maybe a yes or no question or like a this or that type thing. And let's see where you stand on some of these things, all right?
Okay.
Is pineapple a pizza topping?
No.
Does clam chowder belong in a sourdough bread bowl?
No.
I-93 or the 101?
101.
DAWs or ELNs?
ELN.
Really? Oh, okay.
I'm just the most familiar with it, honestly.
Academia or industry?
Ooh. Industry with a caveat that it's more like academia.
Biggie or Tupac?
Ooh. I'm gonna go Pac. And that is strictly more on the delivery side. Like, I just feel like his delivery and like especially the beats he had from like Johnny J, he's the favorite producer of his. Yeah, like the chemistry between them, just immaculate.
Last one, man. Nobel Prize or Grammy?
Now we're going with Nobel. Grammys, honestly, I mean, it's kind of like a popularity contest at this point. Whereas a Nobel Prize, it's like, I think you actually have to do something important to get one. Whereas like a Grammy, like you could just be the biggest fart puffer in the room and, you know, make some really pretentious music and, you know, convince the Grammy committee that it's really important.
When people look back on DJ Grumble 50 years from now, do you want them to remember the molecules that you designed that helped people? Or do you want them to remember you by the beats that moved people?
Man, that's tough, bro. I would try to do both just to put the stake in the ground and being like, all right, I did both. And like, somebody could try to beat that Guinness record, right? Like we solved some major scientific problem and, you know, we went like platinum on an album or something. I'd be content with that. Even some of the stuff I developed when I was in electronic materials is in phones that currently exist, but you would never know it, right? I'd have to tell you, oh, I made this like one monomer that they use to make this one particular package for like a 5G chipset, right? I try to practice gratitude every day, and like I'm grateful for where I'm at right now. Like I'm still blown away by the fact that like even just like the music that I made got as far as it did, because like I was a graduate student just uploading music for fun. You know, I was like, okay, maybe it'll make me some extra bucks, you know, but like I didn't think it was gonna turn into like paying all my bills, you know what I mean? So yeah, I'm grateful every day that I get to do both music and science.
Where can people follow you?
Oh man, I'm super easy to find just because like all my handles are DJ Grumble on every platform except for SoundCloud. My handle is gbeats, GBEATS. But yeah, just like look up DJ Grumble on Instagram. All my music's on Spotify, Apple Music, Pandora. Avery, thank you to all your fans for listening to my music, and thanks for introducing your audience to my music, and thanks for having me on the show. Yeah, man, had a lot of fun just talking chemistry and stuff. So
yeah, man, great. Thanks for stopping by, dude. And
anytime, man. Yeah, anytime you want me back, just hit me up.
Awesome, man. All right, take it easy, bro.
All right, man. You have a good one. I'm going back to the lab.
All right, man.
All right, man.
Take it easy.
Peace. And they're like, what do those guys do? Is it just like they just make like pretty models of stuff? I don't know. That's why I like organic chemistry, is because it's part art and part science. Don't huff your own farts too much either. Like recrystallize it from boiling pyridine followed by boiling DMF. It's like my sperm count is probably like 0 by now.